Welcome to AI Peer Review. Today, we're diving into a really interesting paper. It's from Daniel D'Souza and his co-authors, and it's got this great title, Treasure Hunt, Real-Time Targeting of the Long Tail Using Training Time Markers.
Mm.
Now, look, if you're working with large language models, LLMs, you've probably felt this specific kind of frustration, right? These models are incredibly powerful, trained on just, well, vast and diverse data sets. They can do almost anything. But then you need them to perform on something very specific. Maybe it's a niche use case or a highly specialized domain, maybe a topic that's just, statistically underrepresented and all that training data. The paper calls this the long tail. And when you hit that long tail, these generalist models can really, really struggle. It's like asking a world-class surgeon, a generalist, to suddenly perform some incredibly rare, specialized brain surgery they haven't specifically trained for.
Precisely, yeah. And the current toolbox for practitioners, well, it isn't always up to the task when you hit that problem. Think about prompt engineering or, few shot examples. They can be powerful, sure, but they often place this huge burden on the developer. You're constantly tweaking, experimenting, trying to find just the right phrase or the perfect set of examples. And models can be hypersensitive to tiny prompt changes, right? They react unexpectedly. Or you need this really rigid system prompt just to get somewhat consistent performance. So this paper asks a really crucial kind of foundational question. Can we optimize the actual training protocols? Can we change how we train these LLMs to fundamentally improve both user controllability and their performance on these rare underrepresented cases at inference time? Can we move beyond, the Band-Aid solutions?
And the answer they propose is, well, it's fascinating. It's not about better prompts at inference time, which is where a lot of focus is. It's about building what they call a treasure map directly into the model itself. They do this by introducing these hyper-detailed, task-specific markers during the training process. So instead of just raw text, you're embedding this rich set of meta information, like an internal GPS, kind of guiding the model's understanding from the get-go.
Yeah.
Exactly. An internal GPS, that's a good way to put it. And the results, well, they speak volumes. Their approach demonstrates significant practical gains. We're talking an average lift of about 5.7% in win rates for open-ended generation quality compared to strong benchmarks. But here's where it gets really interesting. That lift jumps to over 9.1% gains in those underrepresented domains.
In the long
tail
tail.
stuff. And if you dig even deeper into specific, really niche tasks, you see relative lifts up to like 14.1% on things like code repair. And an absolutely astounding 35.3% absolute improvement on linked instruction following. So yeah, this isn't just some incremental tweak. It feels like a fundamental shift in how we might guide and control LLM behavior, especially in those tricky long-tail scenarios.
Okay, let's unpack this core problem first. You mentioned the long tail for LLMs. For our listeners, and I know many are probably grappling with this exact issue in their work, what exactly is this long tail problem? Why is it such a persistent pain point?
Well, LLMs are, designed to be generalist. Their training data is this incredibly diverse mix. It covers everything from creative writing, coding, summarizing scientific papers, multi-choice QA. The breadth is just huge. The challenge, though, is that at inference time, when you actually use the model, a user might need performance on a very specific use case, something that's critically relevant to them, but was just barely represented in that massive training corpus. Like imagine you're building an LLM tool for specialized medical diagnostics. The general model might know about medicine, sure, but it probably hasn't seen nearly enough examples of those really specific, rare diagnostic scenarios to be truly proficient. And it's just prohibitively expensive and time-consuming, let's be honest, to go back and retrain these giant models for every single specific niche request. You're basically trying to specialize a generalist without paying the cost of specialist training.
Right. So it's this fundamental mismatch. The training is broad, based on, well, whatever data is available in bulk. But real-world use often demands highly specific, sometimes incredibly rare outputs. And the existing solutions, while useful, they've always felt like a bit of a workaround, haven't they? Like you said, Band-Aids.
Absolutely. Prompt engineering, for instance. Powerful, yes, but it often feels like trying to crack a safe with a whisper. Tiny phrasing changes can completely throw the model off. It leads to unpredictable, brittle performance, requires an almost alchemical touch sometimes. And multi-shot examples, where you give a few examples in the prompt, it's almost like you're creating a tiny bespoke training set on the fly for every single query. And while it works, its effectiveness can depend heavily on things like example order or the exact wording, and it's just incredibly inefficient if you're dealing with lots of different long-tail queries. The paper really highlights these existing approaches put a heavy burden on the developer to anticipate every optimal strategy for a specific model, which, just isn't scalable for complex applications.
Okay, so the paper offers this new paradigm, treasure markers. And crucially, this isn't about tweaking the inference input. It's about embedding the treasure map during training. What exactly are these markers? How do they fundamentally change how the model processes information?
Right. So at its core, the idea is to inject explicit, fine-grained characteristics about the data directly into the training process. Think of it like adding highly descriptive tags or metadata to every piece of information the model learns from. Technically, they condition the output sequence, let's call it Y, given an instruction X, but critically, they add these training markers, M. For our listeners who like the math, the paper shows this as PYXM equals PYXM, yeah. But what that basically means is the model isn't just predicting the next word ye based on the input X and the words it already generated. It's explicitly factoring in these hidden treasure markers M at every single step of generation. So these markers can profoundly influence the output, steering the model's internal state.
That makes it much clearer. Yeah, thanks. So the model is constantly aware of these markers as it generates. They become integral to its understanding. How are they formatted? Are they like special tokens or something else?
They're actually formatted as structured natural language, which is quite clever. For example, a marker might look something like marker list domain sciences, domain language French language, marker list. And then they're encoded with the exact same tokenizer as the rest of the text. So the model just sees them as part of its normal linguistic input. During training, they include them in both the input usually appended to the prompt and in the output, appended to the completion. This kind of dual inclusion really reinforces their importance to the model.
Okay, so the model learns to deeply associate specific characteristics, like French language or sciences domain, with certain generation patterns. Makes sense. And you mentioned a really crucial point earlier. These markers are optional at inference time. How is that achieved, and why is that flexibility so important?
Yeah, that's where marker dropout during training comes in. And it's absolutely critical for this to be practical in the real world. They use dual dropout strategies, dataset level and sample level, but only on the prompt side. Think of it like training a student. Sample level dropout is like occasionally giving the student a homework problem where a piece of info is missing, forces them to infer it from context. But dataset level dropout is much stronger. It's like entire lessons or topics are taught without ever explicitly stating certain key facts. It forces the student to learn to predict and use those facts even when they're not explicitly provided. This double whammy basically ensures the model learns to generate and adhere to markers even when they're missing from the input prompt at inference time. It learns to infer them or even operate okay without them. This stops the model becoming overly reliant on seeing the markers explicitly, gives you significant flexibility. You can provide the map, or the model can try and figure out the terrain itself.
That's a really sophisticated way to build in robustness. So the paper talks about a pretty comprehensive taxonomy of markers categorizing up to 90 unique attributes. That sounds like a truly exhaustive treasure map.
Hmm.
Can you walk us through maybe some of the most impactful categories, the ones our listeners might find immediately useful?
Certainly, yeah, they developed this taxonomy around distinct groups of desired characteristics. And importantly, it was all designed with practical inference time use cases in mind. First up, length. This is incredibly crucial for control. Anyone who's tried to get an LLM to generate a precise number of words knows it can be, well, tricky. So they have markers like length tokens or length sentences for that granular exact control. But they also have broader categories like length bucket for more general guidance. Think concise, medium, or long. Gives you both precision and flexibility.
Right, that makes sense.
Next, quality. Now imagine being able to actually steer the model towards higher quality outputs. Quality is often subjective, but they tackle it. They use quality, which is a FLOPE score derived from their internal reward models, or quality bucket, which ranges from 1 to 4, indicating quartiles, 1 being the highest quality. So you can literally tell the model, hey, give me your best quality output for this.
Wow, okay.
Then there's domain and task. These are absolutely vital for targeting that long tail we talked about. Domain markers like sciences, technology, medical, finance capture those broad knowledge areas, and task markers get really specific. Summarization, code generation, question answering. For coding, they even have code type for specific languages like Python or JavaScript. Super critical for developers.
And it's not just people manually labeling all this data, right? I think you mentioned they used other LLMs like Command R plus N to actually assign these markers to training samples when they weren't already there. That sounds like a massive effort in data enrichment, especially across 23 languages. Building out this granular map must have been intense.
It truly was. And this LLM-driven annotation process is, I think, a bit of a game changer. It means they could scale up creating these markers across millions of examples, multiple languages. It makes the whole approach much more practical. It's basically using one powerful AI to build the foundational knowledge map for another. That's what enables this fine-grained control.
Okay, so once they had this incredibly detailed treasure map embedded in their model, how did they actually put it to the test? Let's get into the numbers. How did they evaluate it?
Right, so they fine-tuned a 7 billion parameter proprietary-based model. They used a pretty big data set, 2.7 million instruction-style examples covering all 23 languages. And they compared three main setups. 1, the baseline, just the model trained without any markers. 2, treasure marked. Markers were used in training, but at inference, the model had to infer them. They weren't explicitly provided. This tests if the model learned to read the implicit map. 3, and treasure marked. Fixed. Markers in training, A and D explicitly hard-coded into the prompt at inference. This tests the model when it has the map right there in front of it.
Okay. And the open-ended generation quality results look pretty compelling. Figure 3 in the paper shows an absolute increase of 5.7% in win rates against Gemma 29B across all tasks. That's a solid improvement just from training with markers and letting the model infer them. Suggests the model's just generally better, maybe.
Yes, exactly. But this is where that long-tail hypothesis really shines. While you get that solid 5.7% boost overall, even in well-represented domains, they saw an even more pronounced gain of 9.1% in those underrepresented domains. Areas like social science, sciences, finance, medical, legal stuff that made up less than 5% of the training data. This really powerfully confirms that the treasure map is effective at unearthing performance in those rare scenarios.
That's huge.
It is. If you're a developer building, say, an LLM for specialized legal document analysis, a highly niche domain, this isn't just marginal. It potentially means you might not need to retrain a massive model on scarce legal data. You can potentially guide a general model to perform like an expert within that domain using these markers.
That really is a core breakthrough for anyone targeting niche applications. I also found the quality control aspect really fascinating. That's figure 4, right? Where you can actually drive the model to generate demonstrably higher quality outputs just by changing the quality bucket marker. It seems like a direct control lever over something that's usually so subjective and hard to manage programmatically.
Absolutely. By explicitly setting those quality markers at inference, they saw win rates jump from about 48.2% up to 56.5%, according to their internal reward model. This isn't just a small nudge. It shows clear, predictable control over a traditionally subjective attribute like output quality. Imagine the implications for, say, content generation or customer service bots where you need a high standard consistently without constant human checks.
Yeah, definitely. And in coding, where specific subtasks can be really niche and complex, Figure 5 shows some impressive gains too, particularly for underrepresented tasks like code repair and code translation. Really hammers home that long-tail benefit.
It's a fantastic illustration. Look, code generation made up over 75% of their coding data. But things like code repair and code translation, much rarer in the training set. Yet, with treasure markers, code repair saw a 14.1% relative gain, and code translation a 6.5% gain. Compare that to only 3.2% for the frequent code generation task. It just shows how this framework disproportionately benefits those infrequent features. It gives a significant performance boost exactly where it's most needed, where traditional methods often fall short.
Yeah. For a developer integrating LLMs, that could mean much more reliable code assistance, especially for those annoying niche debugging or code migration tasks.
Exactly.
Okay, and length control. Another area where LLMs are, let's face it, notoriously bad sometimes. You ask 50 words, you get 200. Table 4 shows truly dramatic improvements here. I mean, going from over a third of responses violating length constraints down to barely over 1%, that's quite something.
The results are honestly striking. For length instruction following, the baseline model messed up the length constraint 36.58% of the time, a huge chunk. The treasure-marked fixed model, where they gave it the explicit length marker at inference, it reduced this to a mere 1.25% violation rate. That's an astounding 35.3% absolute improvement. And even when the markers were just inferred by the model, so no explicit length marker provided at inference, the violation rate still dropped significantly, down to 24.74%. As Figure 2 also clearly shows, this ability to stick to precise length requirements is a huge leap forward in controllability. And interestingly, it even boosted overall generation quality by nearly 7% in win rates. So precision didn't hurt quality. It might have even helped.
That's huge for anyone building, like, automated report generators or maybe tweet summarizers. It turns a common pinpoint into a reliable feature.
Exactly right.
And it wasn't just English, was it? They tested across 23 languages. Table 6 shows significant gains in language control, too. An average absolute gain of almost 11% in line-level pass rates for sticking to the requested language. Crucial for multilingual stuff.
Indeed. It demonstrates the mechanism isn't just an English thing. That ability to reliably guide the model to stick to the requested language, even within a single output, is vital for global applications, maintaining linguistic integrity.
Okay, so beyond these really impressive core results, the paper also digs into some key ablations to understand, how flexible and robust this whole framework is. First, this idea of on-the-fly marker annotation. Can you get another LLM to basically enrich incoming prompts with these markers at inference time without a human needing to step in, sort of automating the map creation for every new query?
Yes, and the results here are incredibly powerful for thinking about real-world deployment. They use Command A, another LLM, to automatically annotate incoming prompts with relevant markers. And what happened? The length violation rate on that Alpacable ALI benchmark dropped even further. It went from 24.74% when the main model inferred the markers itself down to a minuscule 0.75%. So, yeah, drastically reduces violations, but it also boosted win rates by another 2.4%. That's in Table 8. It effectively shows you can get the benefit of having fixed explicit markers without the manual burden of creating them for every single query. Makes the system incredibly adaptable, scalable, perfect for dynamic, context-aware prompting.
That really does suggest exciting possibilities for more intelligent agents. Okay, what about marker interaction? If you add multiple markers, say, I want a specific length and a specific domain, do they combine nicely? Or do they potentially conflict? Do they play well together on the map?
That's a great question. And yeah, they looked into that. In their experiment, which is on Tabor 9, they tried adding a domain marker alongside the length tokens marker for length control. And interestingly, it actually led to a plus 3.5% jump in win rates, even with only a tiny, negligible increase in the length violation rate. This is pretty significant because it indicates these markers can form multidimensional relationships. They aren't just isolated controls. You can leverage them together, suggesting a synergistic effect rather than interference.
So you can define a highly specific treasure at the intersection of multiple map coordinates, basically.
It's a multifaceted target.
Okay, and finally, the impact of that dropout you described earlier, the thing that builds flexibility. How important is it that the model learns to infer markers when they're not explicitly provided? What happens if you skip that dropout step during training?
Dropout is absolutely critical. Table 10 shows this clearly. If you have too little dropouts during training, say, 0% dataset level dropout, the model becomes overly dependent on seeing the markers at inference time. It essentially learns it only performs well if the map is explicitly handed to it, which leads to very low accuracy in predicting those markers when they're absent. The sweet spot they found, around 50–70% dataset level dropout, that's where the model is really forced to learn to effectively infer the missing markers. It's about teaching the model the meaning and context of markers, not just memorizing their presence. And that provides the flexibility and robustness you need for real-world use, where you can't always guarantee explicit marker presence.
Wow. Okay, so this deep dive into Treasure Hunt really shows the power of bringing explicit granular control back into LLMs through these clever training time interventions. It's not just about fumbling around at inference anymore.
It fundamentally moves beyond the limits of purely inference-side prompt engineering, right? It enables fine-grained control over key things like quality, length, language, domain, and crucially, it simultaneously boosts performance on those challenging, underrepresented long-tail cases that frustrate so many of us. Plus, the ability to infer markers or even automate their annotation on the fly offers incredible flexibility for actually deploying this stuff.
So wrapping up, what does this all mean for you listening? For the developer, the researcher, the person trying to build something useful with these LLMs?
Well, consider how this kind of granular, training-driven control could fundamentally change how we design, interact with, and maybe even evaluate future LLMs. Instead of endlessly tweaking prompts or relying on the sort of black box magic of few-shot learning, we might be moving towards a future where user intent is mapped much more directly to model behavior through these explicit, rich internal treasure maps. So here's a thought. How might this deeper understanding of control levers redefine the very architecture of next-generation LLMs? What surprising new capabilities could emerge from this kind of principled intervention during training? Think beyond just better long-tail performance or simple controllability. Could we perhaps see models that dynamically adapt their expertise or even personality by loading different map sections on the fly?
That's definitely a profound thought for our technically savvy listeners to ponder. Thank you for joining us on this AI peer review. Until next time, keep digging for those insights.